Hi guys, I thought I would make a video of me working through a practice of test 3. So there are quite a few problems in test 3 that are asking you to think about the differences between ionic and covalent or molecular compounds. And one of the big differences between these guys is how they behave when they are dissolved in water. So when ionic compounds dissolve into water, they dissociate into cations and anions. So if I take a very stereotypical ionic compound like sodium chloride, often referred to as salt, when that is dissolved in water, it will separate out into the component cations and anions. In this case, it's a 1-to-1 ratio, but if we had something like sodium oxide, then you can see that we're going to get 2 sodium ions and 1 oxide anion. So it doesn't have to be a 1-to-1 ratio, it can be more complicated. So when ionic compounds are dissolved in water, they separate into their component ions. When molecular or covalent compounds are dissolved in water, there are two things that can happen. If your compound is an acid, which we can normally tell from the name that's given, when that's dissolved in water, it'll dissolve to form one or more hydrogen ions and an anion. And the charge on the anion is always going to be negative because it's an anion, but it's always equal to the number of hydrogen ions that are produced. So acids will separate into hydrogen ions and an anion when they are dissolved in water. It is important to recognize, though, that acids are a class of covalent compounds, or what we call molecular compounds. They're just a special class. Now, most molecular or covalent compounds are what we call non-acids, right? Most of them are. So something like this guy, C6H12O6, it's not an acid, it's actually a sugar. When that's dissolved in water, what's going to happen is we just end up with intact molecules. It doesn't dissociate at all. The molecules kind of get dispersed and water fills in the spaces between the molecules, but the molecules themselves don't dissociate in any way. So that's what we've got going on there when these substances are dissolved in water. And it's going to relate to our first question. So, in fact, there's several questions that are like this. It says the names and chemical formulae of some chemical compounds are written in the first 2 columns of the table below. And what I can see here is that none of these compounds are acids, right? Because the names don't end in acid. So they're either non-acid molecular compounds or they're ionic compounds. But when I look at the formulas, I don't see any of these compounds beginning with a metal or beginning with the polyatomic ion ammonium. So what I know is that all of these guys are molecular and they're all non-acids. Okay, so then it says every compound is soluble in water, and you are to imagine that a few tenths of a mole of each compound is dissolved in a liter of water. Okay, so you got like a lot of water. Water is 55.6 moles of water per liter of water. Then it says, write down in the 3rd column of the table the chemical formula of the major chemical species that will be present in this solution. For example, you know water itself will be present, so you can begin each list with the chemical formula for water. So we've got 3 lists here. Let's just call them A, B, and C. And what we know in each case is that we're going to have a bunch of water present, but the question is what else is going to be present. Because these guys are all molecular non-acids, we know that what will be present will be just the intact molecule So we will just write down the formula for each. Don't be fooled in any way by seeing the parentheses there and thinking that that represents the hydroxide anion. It doesn't. Okay. There we are. So that's it. So all that's going to be present is a bunch of water, and then dispersed throughout that water are the undissociated molecules of fructose, propylene glycol, or sucrose, depending on what we're talking about. So that's it. We're just going to write out the names of the formulas next to water. Okay, so looks like we've got something similar. So we're going to have a look at these guys. We're going to decide on the class of the compound. If I look at the first one here, it's got acetone. It's not an acid. It doesn't begin with a metal or the ammonium ion, so it is molecular. But it's a non-acid, right? Okay, we don't have acid in the name, so we know it's molecular. Now, the second two, we can see each of the formulas begins with a metal. So we know that both of these guys are ionic, and they're going to dissociate into ions. The question becomes, what are the ions? So for the first one, we're just going to write water, and then we're just going to write the formula of the compound, and we're going to be cautious not to make a mistake. There we go. Now, for B, we have to figure out what the ions are that are formed. So potassium hydroxide, when it dissociates, is going to form potassium ions. Potassium's in group 1, so that'll be +1. And then hydroxide ions, they've got to be -1. They're in a 1-to-1 ratio. So these are the things that will actually be present. So it'll be water, potassium ions, and hydroxide ions. Sometimes people want to break the polyatomic ion down into its components. Don't do that. If it's a polyatomic ion, the species, the atoms that make up that ion remain bound to one another. Okay, the next one's not too bad because you get the charge of the cation in the name. So we've got FeBr3, and it says it is iron 3+. So we go Fe3+, and then we don't have a polyatomic anion in this case. We have 3 bromides, and we know that they're -1 for 2 reasons. One is the total negatives have to balance the total positives, but the other reason is that bromine is in group 7A, and the halogens always form a -1 anion. So the major species will be water, and then there will be smaller amounts of Fe3+ ions and Br- ions. Okay, so you're getting the idea here. Ionic compounds, we have to dissociate them into their component ions, and covalent compounds, unless it's an acid, we're going to leave it intact. Okay, I told you there were going to be a couple here. So it says the names and chemical formulas of some chemical compounds are given in the table below. That's going to allow us to identify the class of compound. Is it a molecular compound that's an acid? Is it a molecular compound that's a non-acid? Or is it an ionic compound? That's what we're going to use that first bit of data to do. So zinc iodide, the formula begins with the metal zinc. So I know that that guy is going to be ionic. Potassium carbonate. Potassium's a metal from group 1A, so I know that potassium carbonate will also be ionic. And then finally, nitrous oxide. Nitrogen is a nonmetal. This is a covalent compound or a molecular compound. It doesn't contain hydrogen. The name doesn't end in acid, so I know that it's a non-acid and it's not going to dissociate. So what's going to happen is my first 2 compounds there will dissociate into ions when they're dissolved in water, and the last one will remain as intact molecules. So what happens when zinc iodide is dissolved in water? Well, zinc always forms a 2+ ion. It's one of our special cases. Remember we said that Group 1A always forms a 1+, Group 2A always forms a 2+, and then we have some special cases. Aluminum and gallium always form 3+, cadmium and zinc are always 2+, and silver is always 1+. Now we have two iodide ions. Iodine's in group 7A, so the iodide ion has a -1. So when this guy is dissolved in water, the major species will be water, and then we're going to have some zinc ions, and we're going to have some iodide ions. Okay, our next species is potassium carbonate, and it is also ionic. So potassium carbonate. Now it's an ionic compound, and we can see, because we've got more than one non-metal there, that it involves a polyatomic ion. Remember what I said, don't dissociate the atoms that make up the polyatomic ion. Now potassium's in group 1A, we have two of them, and elements from 1A form +1 ions. And then the carbonate anion has a 2- charge. We can look that up in a table of polyatomic ions, or we can recognize that because we've got a total charge of +2, we need a total charge of -2. Again, don't separate out the atoms that make up that polyatomic ion. So in answering this guy, water is going to be there by far in the largest amount, and then we're going to have potassium ions and carbonate anions. And we're going to have twice as many potassium ions as we do carbonate ions, because these guys are in a 2-to-1 ratio. Okay, finally we have to do nitrous oxide, N2O, the stuff that's in whipped cream canisters, laughing gas, and when that's dissolved in water, it does not dissociate. The molecules just kind of spread away from one another, and water molecules fill in the space in between. So the species that will be present here will be water molecules. They'll be the larger amount, what we call the solvent, and then we'll have small amounts of N2O molecules. So there are my 3 answers for that one. Make sure you get all the correct subscripts and superscripts, and the values of your charges have to be correct, or you'll get marked incorrect. Alright, we've got more, and they're steadily getting kind of like more complicated. More ionic compounds, more polyatomic ions, just kind of like a little more challenging to figure out. And what makes this one difficult is that we have a polyatomic cation for the first time. So iron 2 sulfate, it's got iron in it, iron's a metal, so we can fairly quickly tell that this guy is going to be an ionic compound. Then we've got nickel 2 chloride. Again, nickel is a metal, so we know that that's an ionic compound and that it's going to dissociate into its component ions. And then we've got ammonium chloride, and it begins with the symbols NH4, which means it's the cation that is present there is the ammonium cation, and it's a rare example of a polyatomic cation, so that also is an ionic compound. So all of these things, when they're dissolved in water, are going to dissociate into their ions. So now we just got to work out what those ions are and what their charges are. So in the first case, we've got FeSO4, and we're told that it's iron 2 in the name. So again, don't dissociate your polyatomic anion in this case. So these guys must have equal and opposite charges in order to establish neutrality. So the answer for the first one, we've got water. That's going to be there by far in the largest amount. And then we've got iron 2+ ions and sulfate anions. And those guys are going to be in a 1-to-1 ratio. Now for B, we've got nickel 2 chloride. The nickel 2 refers to the charge on the nickel. So the charge on the nickel is 2+, and then we've got 2 chloride anions, each of which has a -1 anion, -1 charge. So the major species present: water, nickel 2+, and chloride ions. And again, we can see that the nickel 2 ions and the chloride ions will be present in a 1:2 ratio due to that ratio being present in the compound. Now finally, we've got to do ammonium chloride. So NH4Cl. When this is dissolved in water, it will, because it's an ionic compound, it dissociates into its component ions, which in this case are the polyatomic cation, the ammonium ion, and the monatomic anion, the chloride ion. So the major species present will be water, ammonium ion, and chloride ion. And for a polyatomic cation, just like for a polyatomic anion, we don't break those atoms apart. All right, so we had 3 ionic compounds there, and we had a polyatomic anion, and we also had a polyatomic cation, so it kind of makes it, a bit more sophisticated than the previous ones. Okay, so this question here is really based on the same principle, but we're going to be looking at the ratios of the different components. So what it says is that you have to imagine a small amount of each compound in the table below, so we've got 2 compounds, is dissolved in water. And then you have to pick a sketch that best shows what the solution would look like at the atomic level. So the first compound here, barium chloride, what I'm going to recognize is that it is ionic. And so what that means is it's going to separate into barium ions, and they're going to have a 2+ charge because barium is in group 2A. And then I'm also going to get 2 chloride ions for every 1 barium ion. So what I'm going to end up with is a solution that contains 2 different types of particles. Let's call them colored in circles and open circles. And they're going to be in a ratio of 1:2, right? So that's what I'm looking for. So I go to my image here, question number 5, here we go. And I have to move the slider across until I have an image where I've got particles in a 1:2 ratio. Now, the water molecules are kind of shaded in the background, so it allows you to focus in on what's going on. So this guy here is a diatomic molecule, and then I've got some sort of monatomic species here, but it's in a 3:1 ratio, so it's not that guy. Now, this has just got separated molecules here. These are tetraatomic molecules. They're both of the same type. This doesn't make any sense. And then here, I've got 2 different things, which is what I do want, but one of them is some kind of monatomic species, and then the other one is a homoatomic diatomic molecule. So, and they're in a 2:2 or 1:1 ratio, so that doesn't work. This is no good. I've got 2 identical heterodiatomic molecules. That's not what I want. I want 2 different monatomic ions in a 1:2 ratio, right? Okay. This is no good. I've got 2 different things, but they're in a 2:2 or a 1:1 ratio. One of the things is monatomic, and then the other thing is a tetraatomic heteroatomic molecule. So that's no good. This is looking closer. I've got 2 different things. They're both monatomic. That's impressive. And they're in a ratio of 2 blue ones to the 4 yellow ones. So 2:4 is the same as 1:2. So it's got to be number 6. Okay. So it's number 6 for this guy. All right, so that's it. So that's what I had to look for, right? I'm looking for 2 different monatomic things in a ratio of 1:2. And that's what I've got there, right? Okay, there we go. They're in a ratio, 2 different things that are monatomic in a ratio of, in this case, 2:4, which is the same as 1:2. Okay, so that one was number 6. Let's look at the other one. Now, NO. NO is a molecule, right? And NO is a covalent compound. It's not an acid. So when it's dissociated in water, it's just going to end up as like separate as molecules. So what does it look like as a molecule? Well, it's diatomic and it's heteroatomic. So I've got diatomic molecules, just one type of thing present, and they're heteroatomic, so two different types of atoms. So that's what I've got to kind of find by moving that slider across. So number one, I do have my heteroatomic diatomic molecule here, but I've got this other thing. That's not correct. This is no good. I've got a heteroatomic, tetraatomic molecule. I want a diatomic molecule. This is no good. I've got two different things. I only want the one thing to be present, and it's got to be this guy, right? This is a heteroatomic, diatomic molecule. There's only one type of particle present. I'm very happy with that. It's number 4. Okay, so there we go. Number 6 for the first one, number 4 for the second one. All right, cool. Let's move on. Okay, so now we're asked to do a conversion between the grams of iron 3 oxide and the number of iron atoms. So I've got to go from grams of Fe2O3 all the way to number of iron atoms. So I've got two different types of things here. I've got Fe2O3 and iron atoms. And whenever I want to go from one kind of thing to another kind of thing, I've always got to go through moles. So what I'm going to do is this. I'm going to go to moles of Fe2O3. Then I'm going to go to moles of iron. And then from there, I can go to the number of iron atoms. Now, if you remember that the conversion factor to go from grams to moles is to multiply by 1 on the molar mass. When you want to go from moles of one thing to moles of another thing, you have to multiply by what we call the mole ratio. And then finally, if you want to go from moles of something to the number of something, you multiply by a number called Avogadro's number. So, can we define these things? What are the things that we need to look up? We get the mole ratio by looking at the formula, so that's easy. We can get Avogadro's number from a list of constants, so that's not a big deal. But we will need to calculate the molar mass of Fe2O3. So I'm going to go ahead and look that up on a handy dandy molar mass calculator. You can calculate it by hand if you want, but the best thing to do is just go to one of these molecular weight calculators. I like this Lentec one. As long as you don't put it incorrectly, you're good. 159.69. 159.69 grams per mole. So from here, we should be good. All right. So we had 80 gram sample, and we want to know how many iron atoms. So set it out nice and neatly. 80 grams of Fe2O3, and our first conversion is into moles of Fe2O3. So we need grams of Fe2O3 on the bottom and moles of Fe2O3 on the top. And what our molar mass tells us is in 1 mole of Fe2O3, we have 159.69 grams. And there we go, our units cancel out, and we know that we have done our first conversion correctly. Our next step is to turn our moles of Fe2O3 into moles of iron. And we're going to use the mole ratio to do this. And according to our formula, like I said, you always, whatever goes up on here goes down here. We can see from our formula though, we get 2 moles of iron every 1 mole of Fe2O3. So they cancel out, and that leaves moles of Fe, which is what we wanted. And then finally, we were going to multiply by Avogadro's number to get the number of iron atoms. And according to Avogadro, it's 6.22 by 10 to the 23 iron atoms in 1 mole of iron. So moles cancels out and it leaves us with iron atoms. So we've done our conversion. So we had 3 conversion factors, 1 on the molar mass, our mole ratio, and Avogadro's number. And when I put it all together, I get the correct units cancelling out how I want, and I'm left with the number of iron atoms. Now obviously in 80 grams of a compound, there's going to be a lot of iron atoms. So let me just pop my calculator up and we'll just do the math on the screen. So there we go. 80 times 1 on 159.69 times 2 times 6.022 second function E23. And so I want to get a big number, right? And I got a big number, 6.03 by 10 to the 23, and I wanted to 3 sig figs according to the problem. So 6.03 by 10 to the 23. There we go. Pretty good. All right. Everybody's happy. Okay. All right. Let's see if we can. Let's do another one. All right. Let's do another one. This is going to be more of the same. I hate to tell you. All right. Here we go. So what do we got? Alright. Okay, the chemical formula for beryllium sulfide is BES. A chemist measured the amount of beryllium sulfide produced during an experiment. So it's the product of the reaction. She finds that 329 grams of beryllium sulfide is produced. Calculate the moles of beryllium sulfide produced. So this is really easy because we're just going to go from grams of beryllium sulfide to moles of beryllium sulfide. And if you recall from the last question, in order to do that, we're going to multiply by 1 on the molar mass. So we do need to look up the molar mass of beryllium sulfide and see what that is, but that's relatively straightforward, right? We just go BES 41.08 grams per mole, and then now we just do our math. So we had 329 grams of beryllium sulfide, and what we just calculated is in 1 mole of beryllium sulfide there are 41.08 grams of beryllium sulfide. So that cancels out and our conversion is relatively straightforward. So you can just go ahead and do that. Alright, 329 times 1 on 41.08. We want this to be given to 3 significant figures, so that's going to be 8.01 moles. There we are. So in this problem, we are told that a chemist determined that 0.015 moles of beryllium participated in a chemical reaction, and we have to convert that to the mass of beryllium. So our conversion is going to be going from moles into grams, and we're doing beryllium. So the conversion factor that we're going to use for this is just the molar mass. So the first thing we're going to need is the molar mass of beryllium, and so you can look that up either in the periodic table or you can go to our molar mass calculator that's online and look that up. So Be for beryllium, make sure you get the correct formula. There it is, 9.01 grams per mole. And now, pretty simple, we have got 0.015 moles of beryllium, and then we want moles of beryllium on the bottom line, so it cancels, and we want to be turning it into grams of beryllium, so we just got to multiply it by 9.01 grams per 1 mole. Moles of beryllium cancels out, and there's our answer. Now, to get the sig figs right, it tells us we have to have the correct number of sig figs. We had 2 sig figs there, and we had 3 sig figs here, so we want to round off to 2 significant figures. So 0.015 times 9.01, and our answer is 0.14. Now I'll just go through this. The calculator answer was 0.135, and that would be grams of beryllium. We want to 2 sig figs. Remember, if it's odd, we go over when we're followed by 5, so it ends up being 0.14 grams of beryllium. Okay, not too bad. On to question 9. Okay, what have we got here? Okay, the chemical formula for methyl tert butyl ether, the clean fuel gasoline additive MTBE, and it's given to us, and it's written in a kind of a interesting kind of way. Let's just kind of break the formula down here. How many carbons have we got? Well, we've got 2 out the front of the parentheses there, and then we've got another 3 times 1, so 2 plus 3, we've got 5 carbons. And then how many oxygens have we got? Looks like we just got just the 1 oxygen. Comes before the parentheses there. And then how many hydrogens have we got? Looking at the formula, what have we got? We've got 3 that are outside the parentheses, and then we've got 3 times 3 for those that are in the parentheses. So 3 plus 9, that gives me 12 hydrogens. So writing out the formula in the more conventional manner, we would have C5H12O. Okay, so that's kind of worth doing sometimes, just so that we can get mole ratios easier. So what it says here is a chemical engineer has determined by measurements that there are 6.7 moles of carbon in a sample of MTBE. How many moles of oxygen are there in a sample? Now, whenever we're going from moles of one thing to moles of another thing, we're always going to multiply by the mole ratio. In fact, whenever we're doing any amount of one thing into an amount of another thing, we always got to go from moles of A to moles of B. We're always going to use the mole ratio. So this is pretty simple. We go 6.7 moles of carbon, and then we've got to multiply by the mole ratio, and that has moles of carbon on the bottom and moles of oxygen on the top. And what we see here is we've got 1 mole of oxygen in our formula for every 5 moles of carbon. So we just got to multiply our number by 5. Moles of carbon cancelled out, leaves us with moles of oxygen. So 6.7 times by 1 on 5. Now, the mole ratio there is an exact number, so we're going to give our answer to 2 significant figures consistent with the 2 sig figs that this guy has. Okay, so pretty easy going there. 6.7 times by 1 on 5 gives me 1.3 moles of oxygen. Okay, on to the next one. What will it be? Probably going to be another stoichiometry problem. Here we go. A chemist weighs out 40.5 grams of barium. So 40.5 grams of barium. And then it says calculate the number of moles of barium. So if we want to go to moles from grams, you have to remember that you've got to multiply by 1 on the molar mass. So we are going to be needing the molar mass of barium, and it's also a much bigger number than what you imagine, this one. So let's go in here. Ba There we are, 137.33 grams per mole. 137.33 grams per mole. So now we can do the conversion. 40.5 grams of barium times by, we've got grams of barium on the bottom there, moles of barium on the top. In 1 mole, we've got 137.33 grams of barium. Grams of barium cancels out, leaves us with moles of barium. Now, how many sig figs are we going to have? The 40.5 there is 3 sig figs. The 137.33 is 5 sig figs. So our answer needs to be 3 sig figs. So 40.5 times 1 on 137.33. And that ends up being 0.295. Now we know it needs to be less than 1 mole because a whole mole weighs 137 grams and we have less than that. Okay, so that makes sense. So pretty simple conversion there from grams to moles, just multiply by 1 on the molar mass. Alright, what have we got here? Okay, so it says an unknown compound has the following chemical formula. It's PT, which stands for platinum, ClX. So what we know is that we get 1 mole of platinum for every X mole of chlorine. That's the mole ratio in this compound. Okay. Measurements also show that a certain sample of the unknown compound contains 5.4 moles of chlorine and 1.36 moles of platinum. So this ratio here that's given here has to equal our whole number mole ratio. So what I'm really saying is in our sample has to have the same ratio of platinum to chlorine as any sample of that compound. So what this means is that 1.36 mole of platinum over 5.4 moles of chlorine is the same as our 1 mole of platinum to X moles of chlorine. So now we just got to solve for what the X is, right? So let's do that, and we can reorganize this. 1 mole of platinum times 5.4 mole of chlorine is equal to 1.36 mole of platinum times X mole of chlorine. So now we just need to divide both sides by 1. So that was just cross multiplying. Now we divide by 1.36 moles of platinum. So 1 mole of platinum times 5.4 moles of chlorine divided by 1.36 moles of platinum. You can see that moles of platinum cancels out is equal to X mole of chlorine. And there you go, we've got moles of chlorine as the units on both sides once we cancel. So let's do the math for that. 5.4 on 1.36. And it ends up being 3.971 mole of chlorine is the same as X moles of chlorine. Now we've got to round this to the nearest whole number. So basically what we're saying here is X equals 4. Okay, so we have a mole ratio of platinum to chlorine of 1 to 4. So what does that mean as far as our formula is concerned? It means that our formula is PtCl4. Okay, we've got a 4 to 1 mole ratio of chlorine to platinum. Not too bad. So we're all kind of working out well. Okay, let's move on and see what the next one is. Getting close, we're on number 12, only got 8 to go after this. Okay, the chemical formula for beryllium sulfide is BeS. A chemist determined by measurements that 0.0550 moles of beryllium sulfide participated in a chemical reaction. Calculate the mass of beryllium sulfide that participates. So what we want to do is turn 0.0050 moles of beryllium into grams of beryllium. And hopefully by now we've recognized that to convert moles to grams or grams to moles, we're going to use the molar mass as our conversion factor. And to do this, we're going to multiply by the molar mass. So we need the molar mass of beryllium, which we previously looked up, but we'll just quickly look it up again. We all know what it is, right? 9.01 grams per mole. There we go. And then we get 0.0550 moles of beryllium. You always know what way up to put your conversion factor because you've got to have what you're cancelling on the bottom and what you want on the top. And so we've got 9.01 grams of beryllium for every 1 mole. And there we go. It's just a matter of multiplying those two numbers together. Now, this guy here, 3 sig figs. This guy here, 3 sig figs. The question just asks give your number to the correct number significant figures, so we're going to give our answer to 3 sig figs. So 0.055 times 9.01 ends up being 0.496 grams of beryllium. There you go. Okay. So, well, we were about right. You know, 0.1 mole, a tenth of a gram, would be about 0.9 grams. Okay, that's good. And we've got about a half of 1/10, so it should be about 0.0. It's perfect. Yeah, it should be about 0.05. Okay, on with the next one. It looks a little scary. We've got a big equation here with lots of coefficients in it. But it's not actually that difficult a question. It says, what is the total number of oxygen atoms on the right-hand side of this equation? Now, a little trick here. Remember that when you have a balanced chemical equation, the number of oxygen atoms, or the number of any atom on the left is going to be exactly the same as the number on the right. So it actually doesn't matter what side you add up. So just kind of pick the easiest one. So it said the right hand side, but I could add up on the left. I think it is actually going to be easy to add up the oxygen atoms on the right hand side because everything is in the one place. So they're all in the sodium aluminum hydroxide there. So what have I got? I've got 4 lots of hydroxide, and then I've got 8 lots of that. So what does that mean? Well, for the 4 lots of hydroxide is going to give me 4 O's, and then I'm going to times it by 8, so that ends up being 32 O's. So, like I said, it doesn't matter whether you do the left-hand side or the right-hand side. Let's do the left-hand side. So 3 times 3, and then we've got 5 times 1. And then finally, we've got 18 times 1. And if you add all of that together, 9 plus 5 gives me 14 plus 18. So 9 plus 5 plus 18 gives me, you guessed it, 32 O's. So it's irrelevant as to whether you add up the left-hand side or the right-hand side. Just do whatever happens to be easiest. Okay, that was pretty easy. All right, this one here we go. Acetylene, this is the gas that we use in welding torches, is often used in welding torches because of the very high heat produced when it reacts with oxygen. So acetylene and oxygen are our reactants, right? And when these guys react, they make carbon dioxide and water vapor. Now, some people, when they were writing these balanced reactions from descriptions of the reaction in the past, have got the reaction reversed. So you always want to be really clear what are the reactants and what are the products. And sometimes they mention the products first. So you want to be very clear that you understand what is going on. Products are produced, reactants react. Okay, so now this is no good to us unless we balance it. So let's balance for carbons first. So carbon, I've got 2 on the left. I've got only 1 on the right at the moment, so I need to times that by 2. And now carbons are balanced. And then hydrogens, I've got 2 on the left and then I've got 2 on the right, so hydrogen is balanced. And then oxygen is always the troublemaker because it's a diatomic element. I've got 2 on the left, but how many have I got on the right? 2 times 2, that's 4, and then another one there, that's 5. So I'm going to have to multiply this guy by 5 on 2. Now, we don't like to have fractions, and so now oxygen is balanced, but we don't like to have fractions in our equation, so we're going to multiply everything by 2. So that's going to become 2, that's going to become 4, that's going to become 2, and that's going to become 5. So now we've got a balanced equation. Okay, so on with the math. It says calculate the moles of water produced, so the moles of these guys produced, by the reaction of 0.6 moles of acetylene, 0.60 mole of that guy. So this is mole of one thing into mole of another thing, so the conversion factor that we're going to use is the mole ratio. Whenever we're converting from amount of one thing into amount of another thing, we're always going to convert our first thing into moles and then apply the mole ratio to get the moles of the second thing. So we got 0.60 moles of acetylene times, and we need a mole of acetylene on the bottom, and then we want moles of water on the top, and it's pretty simple. It's 2 on 2. I'm not going to change our number, is it? It's a 1-to-1. A 2-to-2 is the same as a 1-to-1 mole ratio, so that's going to be 0.60 moles of water. So the key thing is you can't do that without a balanced equation. You have to balance the equation. It says calculate the moles of water produced by this reaction. Be sure your answer has a unit symbol, and if necessary, round to the correct sig figs. So let's make sure we got everything correct there. We started with 2 sig figs, we've ended with 2 sig figs, that's good. And then the abbreviation for moles is MOL, so everything looks good there as far as answering the question, and Alex isn't going to complain. Alright, let's move on. We're whizzing through them. Here we go. What have we got here? Alright, it says wine goes bad soon after opening because the ethanol, that's the type of alcohol that you can drink that will get you drunk, the ethanol in it reacts with oxygen from the air to form water and acetic acid. And acetic acid is the sour acidic component in vinegar. Alright, so we need to write a balanced equation for this. So it is the ethanol reacting with O2 to make acetic acid you get all the formulas correct, and water. So let's have a look at our atom count. Carbon, I've got 1, 2 on the left, 1, 2 on the right, so that was easy. Hydrogen, they're kind of spread out a little bit here. I've got 3 plus another 2, that's 5, plus 1 more, that's 6. And then on the other side, I've got 3 plus 1, that's 4, and then another 2, that's 6. So both carbon and hydrogen are balanced. Now I've got to work on my oxygens, and we know that oxygen can often be a troublemaker, right? So I've got 1, 2, 3 oxygens on the left, and then I've got 1, 2, 3 oxygens on the right. So everything is balanced. There's nothing there that's not balanced. So the nice thing is all of my mole ratios are 1 to 1 to 1. Okay, let's have a look here. Now it says what mass of ethanol is consumed by the reaction of 2.67 grams of oxygen. So I got 2.67 grams of this guy, and I want to know how many grams of that one is consumed. Now remember what I said, whenever you're converting from amount of one thing to an amount of the other, you have to first go into moles, and then you've got to apply the mole ratio. So how we're going to do this problem is like this. We're going to go from grams of oxygen to moles of oxygen. And at that point, we can apply our mole ratio, and we can go to moles of ethanol. Once we've got the moles of ethanol, we can then go to grams of ethanol. So that's what it's going to look like, all right? So the conversion factor between grams and moles is the molar mass, so we're going to multiply by 1 on the molar mass of O2 there. To go from moles of O2 to moles of ethanol, we're going to multiply by our mole ratio. And then we want to go from moles of ethanol to grams of ethanol, so again we're going to multiply by our molar mass. So we need 2 molar masses here. We mean the molar mass of O2, and we also need the molar mass of our ethanol. So the molar mass of O2, I'm just going to speed this up, is 32.00 grams per mole. And then we're going to look up the molar mass of our ethanol. So sometimes they have the compounds in here. It's really up to you if you want to take advantage of that feature. There we go, 46.07. 46.07 grams per mole. So it looks like we're in business at this point, and our mole ratios are really easy in this case. We get 1 mole of ethanol for every 1 mole of O2 according to our balanced equation. So we've got 2.67 grams of O2. We're going to multiply that by 1 on its molar mass. So we need grams of O2 on the bottom and moles of O2 on the top, and we get 1 mole of O2 for every 32.00 grams of O2. So that does our first conversion. Now we've got to multiply by our mole ratio, which in this case is trivial. According to our balanced equation, we get 1 mole of ethanol for every 1 mole of O2. So again, moles of O2 cancels, and we've done our second conversion. And then finally we do our last conversion. So we need mole of ethanol on the bottom here, and we need grams of ethanol on the top, and that's just our molar mass. So our molar mass is 46.07 grams for every 1 mole of ethanol. So moles of ethanol cancels out. So when we do this math here, we need to round everything to 3 sig figs at the end, because our conversion factors here, our mole ratio is always exact, so it has infinity significant figures. Our other conversion factors, though, our 2 molar masses have 4 sig figs, so they're not going to determine the significant figures. So 2.67 times 1 on 32, you're going to have to multiply by 1 on 1, and then multiplied by the molar mass of our ethanol, 46.07. There we go. So to 3 sig figs, we end up with 3.84 grams of ethanol. And there's our answer. Okay, not too bad. Ready to move on to our next one. Now, when you're taking your test, I recommend that you kind of do the easy ones to begin with. You know, that's going to kind of just a good practice. I think it makes things a lot easier for people to do that. So that's just what I would recommend. So, you know, if you look at a problem and it just scares the daylights out of you, move on to the next one and see what that offers, and if that's a little easier at all. All right, here we go. Get the next question squared up. We're getting there. Question 16. Oh, it looks like it's about this acetylene again. Okay. Well, we know our balanced equation from this. We wrote it down earlier, so we would be able to we wouldn't have to go through the hassle of writing that out. So it says acetylene gas is often used in welding torches because of the very high heat produced when it reacts with oxygen, producing carbon dioxide and water vapor. Calculate the moles of oxygen needed to produce 1.5 moles of carbon dioxide. So you're going to begin with your balanced equation again. I'll kind of rush through that. So C2H2 plus O2 are our reactants, and then that makes carbon dioxide and water vapor. And I don't know if you recall, but it was 2, 5, well, let's just do it all again just for the practice, but it was 2 of those, 5 of those, 4 of those, and then we had 8 and 2 of those, I believe. Yes, that works out just great. So just double check that. Carbon, 2 times 2, that's 4. We've got 4. Hydrogen, 2 times 2, that's 4. And then 2 times 2, that is 4. And then oxygen, got 5 times 2, that's 10 on the left. And then on the right, 4 times 2, that's 8, plus another 2, that's 10. Now, you guys would have already have that balanced equation written down previously. So we want to know the moles of O2 required to make 1.5 mole of CO2. So whenever we're going from moles of one thing to moles of another, how are we going to do it? We're going to multiply it by the mole ratio, all right? So 1.5 mole of CO2, and we want to turn that into moles of O2. So we need moles of O2 up there, and we need moles of CO2 here. And from our balanced equation, we see that we get 5 moles of O2 for every 4 moles of CO2. And so there we are, leaves us with moles of O2. So 1.5 times 5 on 4 ends up being 1. And we want 2 sig figs here, so I'm going to round that off, 1.9 mole of O2. There we go. All right. Not too bad. So converting from moles of one thing into moles of another, you always just multiply by your mole ratio. Okay, so moving on to the next problem, it's a similar kind of scenario. You're given a written description of an equation which you'll need to balance, and then you'll have to do some kind of calculation. So it tells us that nitrogen dioxide and liquid water react. So they're going to be our reactants. So it's going to be NO2 plus H2O. And then it says they react to form nitric acid, HNO3, and nitrogen monoxide. So I can kind of already see that there's some potential difficulties here, because I can see that the nitrogens don't balance, I can see that the hydrogens don't balance, and I can also see that the oxygens don't balance. So it's going to be a bit tricky. One of the things that you might do, rather than try to work through this and to balance it by hand, so to speak, is that you might choose to use an online equation balancer. So there's a variety of these, but if you go to calculators at the Lentec one, you can find you can probably find one there, but the one that I really like is the one that's at webqc.org, and there it is. And when you go there, webqc.org, there are a bunch of chemistry tools, and the very top one is the chemical equation balancer. Okay, and it's a free service, so it tends to have a lot of, it has a lot of ads that pop up, so be aware of that. Okay, so what do we want? NO2 plus water gives HNO3 and NO. So NO2 plus, oh, and there it is. It automatically gives it to you because it's such a common equation. So there it is. It's a 3, 1, 2, 1. 3, 1, 2, 1. All right. So 3 of those. 2 of those. And 1 of those. And sure enough, everything balances, right? So nitrogens, 3 on the left. 2 times 1 plus another 1, 3 on the right. Oxygens, 3 times 2 gives me 6, plus another 1 gives me 7. And then up here we go, 2 times 3, that's 6, plus another 1 gives me 7. We've only got one atom type left to balance, and that's hydrogen. 2 times 1 there gives me 2 hydrogens on the left, and then 2 times 1 here gives me 2 hydrogens on the right. So that balances nicely. So now we're ready to do our math. And the question says, suppose you have 1 mole of NO2, 1 mole of that guy, and 11 moles of H2O. 11 moles of H2O. And I immediately think, oh, I know what's going on here. This is going to be a limiting reactant problem. And so what I'm asked is, it says calculate the largest amount of HNO3 that can be produced. And the answer, it's asking you to give it in moles, and you're told to go to the nearest 0.1 moles. So what we're going to do is we're going to say, okay, what would happen if all of the NO2 was reacted? How many moles of HNO3 would I get? So I'm going to go 1 mole of NO2, and I want to turn that into moles of HNO3, so I have to use the mole ratio, right? Whenever I'm going from moles of one thing to moles of another, I use the mole ratio. So I know that I get 2 moles of HNO3 for every 3 moles of NO2. So what do I get now? Moles of NO2 cancel out, and so I've got 1 times 2/3, so that would be 0.7 moles of HNO3 if I reacted all of my NO2, right? That's all I would get, would be 0.7 moles of it if I reacted everything. Now I rounded that off to the nearest 0.1, right? Because that's what they said, so that's what they said to do. Okay, now let's move on to the water, and I've got 11 moles of water, and I can see from my balanced equation that I get 2 moles of HNO3 for every 1 mole of water. So 11 times 2 is going to give me 22.0 mole of HNO3. Now, I can't make 22 moles of HNO3 because as soon as I make 0.7 moles of HNO3, I've used up all of the NO2. So the maximum amount of HNO3 that I could make would be 0.7 moles of HNO3, and that has the correct number of significant figures. As soon as I've made 0.7 moles of HNO3, I'll find that I've run out of NO2. Now here's the cool thing. When I go to my equation balancer here, I can do these limiting reactant problems, right? And what we saw was that we had, 11 moles of that guy, and then we had 1 mole of the other one. Whoops. 1 mole of the NO2, and it highlights what the limiting reactant is, right, in pink here, and it tells me the moles of the HNO3 and the moles of NO that I can produce, and sure enough it ends up being 0.6666, just like I calculated, and you would, to the nearest 0.1, that would be 0.7. So using one of these online equation balances can really be a nice tool to double check your math. You don't want to become too reliant on it, because eventually you're going to have to be answering these problems with no notes at all and no online resources. So yeah, but that works well, all right? It's a great little tool, that one. webqc.org. That's the website. All right, we're almost done with this practice test. We're on to question 18. Pretty good. Okay, we got a big formula here. So it says this is the chemical formula for talc, the main ingredient in talcum powder. So it makes me think that we've got something with lots of coefficients here. It's going to be about mole ratios, I think. And it says an analytical chemist has determined by measurements that there are 1.2 moles of silicon in a sample of talc. How many moles of hydrogen are there in the sample? So again, what I would do is go through and I would write it out so that it has no parentheses. And so you can very easily see what the mole ratios are. So 2 silicons times by 2, so we've got 4 silicons. And then oxygen here, we've got 2 times 5, so that would be O10. And then we've got another set of oxygens, 2 there. And then we've also got 2 hydrogens. So collecting the oxygens together, we could write this formula for talc, Mg3Si4O12H2. So by writing it in that way, it makes the mole ratios really easy to figure out. Now we want to go from 1.2 moles of silicon through to moles of hydrogen. So we know that we're going to have to multiply by a mole ratio, right? When we go from moles of one thing to moles of another, we have to multiply by a mole ratio. And that mole ratio has to have moles of silicon on the bottom, and it has to have moles of hydrogen on the top. So we can see here that we get 2 moles of hydrogen for every 4 moles of silicon. So 1.2 times 2 on 4 is going to give me 0.6 mole of hydrogen. Now we need to be cautious to have our correct significant figures here. This number here has 2 sig figs. This has infinity sig figs. That is, our mole ratio is exact. So our answer should have 2 sig figs. So we want to make that 0.60 moles of hydrogen. And there we are. All right, so onwards to question 19. Let's see what we've got here. Okay, this is looking like an equation written out as a sentence that we're going to have to balance. So it says solid aluminum, okay, and chlorine gas, okay, react. So they're our reactants, and they form solid aluminum chloride. So I'm going to need to get this to balance, right? And what I can kind of see immediately is that the chlorines are going to be the issue here. So on the left, I've got 2 chlorines, and on the right, I've got 3. And what I'm going to do is multiply the right by 2. That will give me 6 chlorines, and then I'm going to multiply the left by 3. So that got those guys to balance. And now I'm going to work out aluminum, and on the left I've got 1, and on the right I've got 2, so I'm just going to give myself 2 aluminums. And then now everything balances. Okay, once I'm armed with a balanced equation, then I can go on and do the math. So then it says, suppose you have 2 moles of aluminum, okay, and you have 1 mole of chlorine, okay. Calculate the largest amount of aluminum chloride that can be produced. So again, it's a limiting reactant problem. I've got to go from moles of one thing into moles of another. What I'm going to do is I'm going to calculate how many moles of product would I get if all of the chlorine was consumed, and then I'm going to calculate how many moles of product I would get if all of the aluminum was consumed. So 2 calculations. Whatever gives the smallest yield, that's my answer. So here we go, 2.0 moles of aluminum. I want to turn that into moles of aluminum chloride. So I need moles of aluminum on the bottom, moles of AlCl3 on the top, and I get 2 for 2. So if all of that aluminum reacted, I would be able to make 2 moles of aluminum chloride. Okay, now there's no guarantee that all of the aluminum will be able to react if we don't have enough of the chlorine. So I got 1.0 moles of chlorine, and I want to turn that into moles of aluminum chloride. So I've got to multiply by the mole ratio that has moles of chlorine on the bottom and moles of aluminum chloride on the top. And according to my equation, I get 2 moles of aluminum chloride for every 3 moles of chlorine. So that would give me 0.67 moles of aluminum chloride. So this number is the smallest of the 2. So what's going to happen is the aluminum will react with the chlorine. It'll keep reacting. Aluminum chlorine will get consumed. I'll produce 0.67 moles of aluminum chloride, at which point I would have run out of the chlorine and the whole reaction will stop. So this is the maximum amount of aluminum chloride I can make. This had 2 sig figs, and so that's why my answer here has 2 sig figs. Alright, we are so close. On to our last problem, question 20. Alright, one goes bad soon after opening because the ethanol dissolved in it reacts with the oxygen. We've seen this, haven't we? CH3, CH2, OH, plus O2 are our reactants. What do they form? They form water and acetic acid, CH3COOH. So you have to get that from the problem. Now, we've already done this reaction, so we don't have to go through balancing it again. We can just look back on our notes, and remember it's all 1 to 1 to 1 to 1. So that's really easy. So we can actually go on and do the math now. So it says calculate the moles of water produced. So we want moles of water, that's what we're after, by the reaction of 2.4 moles of oxygen. So 2.4 mole of O2. So how do we go from moles of one thing to moles of another? We've got to multiply by our mole ratio, which in this case we really don't need to work very hard at because everything is 1 to 1. So if you're sharp, you'll realize that the answer is already 2.4 moles of water. But let's just go through the math just for the exercise. So 2.4 mole of O2, I'm going to multiply it by the mole ratio. That has mole of O2 on the bottom and a mole of H2O on the top. And according to our balanced equation, we get 1 mole of H2O for every 1 mole of oxygen. So one can see that what am I left with? 2.4 mole of H2O. There we go. All right, so that ends the video summarizing the practice test.